Okay, so today we're going to look at the last part of the, this part of the units, trigonometric functions unit, and it's on trigonometric identities. Last year, you looked at trig identities and you looked at the process of doing the identities, which is the same process now as it was last year. It's just that now we have more identities as basic identities that we can use in order to prove our identities. So here on the first page of your handout, I've given you the identities that we can use in order to prove the identities that are given to us. So the general process of proving an identity is that first you make a left side and right hand side of your identity, write them out. You're not going to put the equal sign until you've actually proven that the left side is equal to right side. You start from the side that looks more complex and try to get to the other side. Now, in doing that, you can use any of the identities that you can see on this page, or you might need to do some algebraic work, such as finding common denominator, multiplying by conjugate, for example, or finding and doing factoring, for instance, right? So this is a process. Now, some of the questions are easier, some are harder, but you get good at it by doing practice. So let's look at some of these identities that we know, and the identity page, basic identities are going to be provided to you for the test as well. So the reciprocal identities, we know them. We know that cosecant is one over sine. And generally, when we are writing we are trying to prove, in many cases, we want to write them in terms of sine and cosine. So if you have cotangent, secant, cosecant, you might want to change them into the primary trig ratios. Pythagorean identities, the most famous one that still we use a lot is the sine squared plus cos squared equal to 1. That's the one that you should always know. There is a lot of application of that in proving identities. There is one that is tan squared plus 1 is equal to secant squared, and 1 plus cotangent squared, which is equal to cosecant squared. Quotient identities, these are also very useful. Many times that you have tan, we want to write them as sine over cosine, or if you have cotangent, we want to write them as cosine over sine. Okay. Reflection identities, sine negative theta equal to negative sine theta, and cos negative theta is equal to cos theta. I've already explained that to you guys. That's why that's the case. If this is angle theta and this is angle negative theta, cosine theta deals with x over r. Now, if you're dealing with theta, x is positive, but for angle negative theta, x is still positive, so their value is going to be the same. However, for sine, because it's y over r, if you're dealing with angle theta, y is positive, but for angle negative theta, y is negative. So that's why it would be sine of negative theta being negative sine theta. So some of these identities are just common sense. The co-function identities also, it might seem confusing, but really what it's telling you is that I mentioned that to you as well, is that when you're dealing with complement angles, sine of one is equal to cosine of the other one. So imagine if your angle is, for example, theta is pi over 3, when you do pi over 2 minus pi over 3, you will get pi over 6. So sine of pi over 3 is same thing as cosine of pi over 6. So again, it's something that makes sense, and we've already gone through it. Then we have our compound angle formulas, which again, you should have them memorized. You should know them because you use them so much, but even if not, it's there. Then double angle identities are used when you're dealing with like twice of the angle. So for example, cos 2 theta, cos 2a, or sine 2 theta, or sine 2a. One thing that's important to know that when you have, for example, sine 2 theta, this is not going to be the same thing as twice of sine theta. That's not the case, so make sure you never do that. You have to deal with double the angle, then find the sine of that, which these identities are useful. This is used a lot, and yeah, for cos 2a, any of the three can be used, but sine 2 theta or 2a is used a lot. So the Pythagorean identities are used a lot. The reciprocals are used a lot. Any of the compounds could be used a lot, and especially sine 2x is used a lot as well. Anyway, so these are the ones that you can use. Now, obviously, there are other identities as well. Like if you go and search the internet, there's going to be a number of identities. But you can, the questions that we give you, you can only use these identities. And sometimes we might ask you to actually prove one of these identities, right? And as you can see in the last question on the handout today, it's asking you to prove tan A plus B is equal to tan A plus tan B over 1 minus tan A tan B. And obviously, to do that, you cannot just say, oh, it's one of the identities that we have. So therefore, this is it. Okay? You need to go through the process and use the other identities to prove that. Anyway, let's take an example. So let's prove the following identity. So 1 minus cos squared x times cosecant x equals to sine x. So as I said, we make a left side and right side. So my left side is 1 minus cos squared x times cosecant x. And my right hand side is sine x. I want to show that these are equal to each other. And I'm not going to put an equal sign until I've proven that these two are equal. That being said, we need to pick the side that is more complex and work with that. So which side is more complex? The left hand side. Like right hand side, sine x. There is nothing I can do with sine x. Sine x is as easy, as simple as it gets. So I need to work on the left hand side. So what can I do on the left hand side? Well, one thing I can do is that cosecant x, that's a reciprocal identity. I can replace that with 1 over sine x. Okay? Now what else I can do? Okay? So 1 minus cos squared x. Is there anything you can do there? If you look at the identities, we have an identity which is, as I said, it's used a lot, and the first Pythagorean identity. We know that sine squared x plus cos squared x is equal to 1. Now imagine if I take the cos squared x to the other side, I get 1 minus cos squared x equal to sine squared x, which is exactly what I have here. So I can replace that with sine squared x. Now, the square and that cancel out, so I'm left with sine x times 1, which is just sine x. And on the right hand side, I have sine x. So they're equal. Now, you would say, therefore, left side is equal to right side, and you put QED at the end, which shows that it's essentially it's telling you that it's proven as it was requested. Okay, so I want to see that left side equal to right side and QED. Okay, fairly simple. Let's get the next one. So we have 2 cos x cos y equal to cos x plus y plus cos x minus y. So again, I make my left side and right side. My left side is 2 cos x cos y. My right hand side is cos x plus y plus cos x minus y. Now, which side do you suggest me to start working with? Left or right? Correct, right. Because left hand side, it's just 2 cos x times cos y. It's not squared. They can, let's say if I had cos squared x, I could have replaced it with 1 minus sine squared. But I don't have that. There is nothing I can do with that side. But on the right hand side, I can see that we have compound angle formulas. So working on that, the first one would be cos x, cos y, minus sine x, sine y, plus, now again, same thing, cos x, cos y, this time plus sine x, sine y. Now, you notice anything? So here you have minus sine x sine y. Here you have plus sine x sine y. So they cancel out each other. They add up to 0. So you have cos x cos y and another cos x cos y. Two things that are like each other, they add up, and you get two of them. Apple and apple makes two apples. So cos x cos y and another cos x cos y will make two cos x cos y, which is the same thing as what I had on the other side. So again, therefore left side is equal to right hand side, Q, E, D. Okay? So I want you to take a moment, look at these two examples that we did, make sure you completely understand them, then go and try to do part C, and once you did, come back here and check your solution. So pause your video, go do part C, and then come back. And this is very important because it's all about practice, and don't give up too easy. Spend some time, think about it, and try to do it. Okay, so pause the video, please. Okay, so I didn't actually finish this question, so I did part of it, and then we're going to continue with it. So clearly, left-hand side is a more complex side, so we start working with that. I'm going to leave the sine squared x for now, and then cosecant squared x and secant squared x, I'm going to change them, use the reciprocal identities, and replace them in 1 over sine squared x and 1 over cos squared x. Now I have two fractions that are added to each other. I cannot add them until I find the common denominator. So essentially in the next step, I just find the common denominator, which is sine squared x cos squared x, and then I have to multiply 1 with cos squared x for the first fraction and 1 by sine squared x for the second fraction. So now I have sine squared x bracket cos squared x plus sine squared x over sine squared x cos squared x. Now, what do you suggest me to do? Is there anything that comes to your mind? Exactly. Again, this is the Pythagorean identity. We know that that's equal to 1. So I'm going to end up with 1 over. Another thing that happens is that you're multiplying this sine squared x by this whole fraction, and there's a sine squared x in the denominator. Whenever there's a multiplication, I can simplify. So the sine squared x and sine squared x cancel out. So I'm left with 1 over cos squared x, which we know that secant squared x. And that is what I had on the right hand side. So again, therefore, left side is equal to right side, Q, E, T. Okay? Now, as you can see, even in the few examples that we've done, that first Pythagorean identity comes very handy. So in one form or another, as an addition or subtraction form, you got to make sure that you know it and you can use it a lot. Okay? So again, take a moment, make sure you understand this, and once you're good with that, go try to do the next one yourself, and then come back and check your work. So again, pause the video, do the next one, and remember, don't give up too easy. All right, so again, this one, I did not finish it again, but did enough, then we can continue from this point. So again, left-hand side is more complex than right-hand side, so we work on the left-hand side. There are a bunch of secondary ratios here. Okay, so what I need to do is I need to use quotient identities to change them to primary trig ratios. So I will have 1 plus 1 over cos x over sine x over cos x plus sine x. Now again, in both the numerator and the denominator, I'm dealing with addition of fractions, which again, I cannot add them until I find the common denominator. So cos x, for the numerator, cos x is the common denominator. So I need to multiply 1 by cos x, and the 1 for 1 over cos x stays the same. So I'm left with cos x plus 1 over cos x. All of it over, and I use the blue line for the main fraction that they have. Find the common denominator of the denominator. Cos x is the common denominator, so I will have sine x plus sine x cos x. Now, what can I do next? I essentially have a fraction divided by another fraction. So if it confuses you, write them beside each other with a division sign between them, which then, because it's two fractions divided by each other, you change it to multiplication and you flip the second fraction. Either way, if you do that, you will see that you end up with one of the cos x being in the denominator and the other cos x being in the numerator, so they can cancel out. Or you can just cancel them out here if you see that. Okay? So the cos x gets canceled out. Now, I'm running out of space here, so I'm just going to go continue here under the right-hand side, because I'm not going to do anything with the cosecant x. So I'm left with cos x plus 1 in the numerator, and in the denominator I have sine x plus sine x cos x. Is there anything I can do there? Exactly, a factor of sine x. So if I factor out sine x, I will be left with 1 plus cos x. Now, do you see anything? Exactly. 1 plus cos x is both in the numerator and in the denominator. Remember, I cannot just, for example, cancel out cos x because it's cos x plus 1. If it was multiplication, I could. But right now, it's the whole term that is the same. And there's a multiplication in the denominator between sine x and that. So I can cancel that out. So I'm left with 1 over sine x. And we know that 1 over sine x is cosecant x. So again, left side is equal to right side, Q, E. Okay? So, again, make sure you go over it, make sure you understand this. These are the more basic ones that we do. Now, we're going to spend 2 days on trig identities, and next day we're going to work on more complex ones. But for now, make sure you do part F yourself. Again, it is one of the identities that we have, but they're asking you to prove that identity, meaning that you cannot say this is one of the identities that we know. You need to use other identities to prove that. So work on that, and we can check that next day in class. Okay?